want to remind you that these things, I will use them from time to time. If you don't have one, and you have a smartphone or a laptop or something like that, you can use that instead. Should I show you? How many people do not have a clicker but do have a web-enabled device of some sort with them? That's huge. Okay. Do I need to show you or can I just tell you? Let me just tell you. You go to the class page, which you can either get to through Blackboard or go to this web page. If you're typing all this crap, you can put a clicker after it, or there's a link on the front that says something like for clicking without a clicker or something like that. Okay, so you can just open that page, and then there's a link about something like that. Okay, I can put it up. Oh, sorry. So in fact, since you have your clickers here, let's have our first clicker question. So A is also the same as 1. Should be 41. Give it a try. You can still do it. Alright, so I'm going to start. And there's people answering. Yay! So the way the clickers are graded, by the way, you get 1 point for answering and 1 point for answering correctly. If you, this might be correct, right? Because if you have, so you should be able to figure out the difference between these two things. For some of you, this is the right answer, and for some of you, this is the right answer. Yeah, yours. Oh, yeah, because I'm stupid. Thank you. So for those of you who don't have one, I screwed up. Thank you for reminding me. I have to launch a web browser and start the question. Duh. So for those of you that don't have clickers, it will say there's no question open because the network doesn't like me right at the moment. But it will. So please be patient. Okay, so for those of you that don't have clickers, if you click the try again button, you should be given a choice. Yeah? The question doesn't come up. There's the question. It just says if you don't have a clicker and you're using a smartphone or something, you should have a bluish page and it should say enter your answer and also enter your ID number. Okay, did everybody manage to figure out to answer that? I have 97 responses with clickers. You just press the number and then you press 1, 2, or 3, and you can press the little thing in the center that says send. And then you should have a little smiley face. If it has a little smiley face, it means I got your answer. For those of you with web phones, it should say I took your answer. Okay, everybody's answered, right? Except him. He hasn't. That's okay, don't worry. You'll get a chance later. Okay, so I'm stopping this question now. And so I can see here, I'm not going to put it up unless it matters. 99% of you answered number 1. 1% of you answered what? And those of you with phones and whatever, I don't get to see your results till I go back to my office. You should have all answered no. If you answered yes, well, I guess yes could be correct. It just means not with you. But anyway, okay. All right, so I will do this, not stupid questions, well, a lot of stupid questions like this too, as we go. But this is just sort of warm up. I won't necessarily ask clicker questions every 5 minutes. I may only ask 1, I may ask 0, I may ask 10, whatever. The point of this is to just get you to interact and talk to each other and do stuff. Okay. Yeah. Oh, thank you. Okay, so now we need to do some calculus. Well, there was one other administrative thing and I just forgot what it was. Okay, so the WebAssign homework. There is a homework assignment on WebAssign. It's up. It's been up for a while. It was due on Wednesday at 9 a.m. Because of the hurricane, I added a couple of extra days. It is now due far too early Saturday morning. This means do it before you sleep on Friday night. If you don't go to sleep on Friday night, well, then do it before 9 a.m. Saturday morning. But do it. And if you do, any questions that you answer, I don't know, early. By the original due date, give you extra credit. So the grading on the, I explained this last time, but so don't be confused. The way the grading works is if you answer right the first time, you get full credit. If you answer right the second time, you get 1/2 credit. If you answer right the third time, you get 1/3 credit, and so on. But if you answer right the second time, but early, then you get more than 1/2 credit because you get a bonus on your 1/2 credit. You get 3/4 credit. Yeah?
Like, do the courses like put in time, like in which you were like we did it 7 days before.
No. If it's more than 2 days before the due date, you get the credit. You get the bonus. So you don't get a bonus over doing it right now versus waiting until Monday. Generally, if you do it over the weekend, because they're usually on Wednesdays, you get the bonus. But if you wait until Monday or Tuesday, you don't. So the main point of the bonus is to get you to think about the problems, do those you can do, and then worry about those that you have trouble later. I know there was another, but I can't remember what it is. So is there anything else? You don't know what I covered. All right. By the way, this is Professor Bonifant. I don't know why she's here, but she is. She teaches the other lecture at 5:20. If for some reason you don't want to come to this lecture anymore because I seem too disorganized, go to hers. Okay, so we need to do some math now. I know it seems confusing, but we'll do it anyway. I don't need to say that. So, what's calculus? Anybody know? Nobody can tell me? Yeah. Well, kind of. Not really. So he says study of rates of change. That's not wrong. Nobody will get what I'm trying to get here, but... so what calculus, anybody else have an idea? So you're right than most. No? Nobody knows what calculus is? You've all had at least a semester of calculus and you don't know what it is? He knows. He's the only one that's been to class. Yeah. Okay. Or rock. Actually, calculus means rock. Yeah. So, okay. So what it is about, I mean, the big idea in calculus, the huge idea in calculus is that you can understand macroscopic stuff by knowing microscopic detail. That doesn't tell you what calculus is, but that's the big idea. This is the big, amazing breakthrough that Newton and Leibniz had. Newton was supposedly sailing on a river, and he wanted to understand how his boat was floating on the Thames or something, and he wanted to understand why his boat was moving, and he was looking at the currents. and realized that the currents were pushing him, and if he just knew how all the currents fit together, he would know where his boat was going to go. And this is the big idea that makes calculus work. And the way that we understand this microscopic detail in modern days is via the notion of a limit. The limit, probably in many, many high school classes and so on, and in fact in college classes, a lot of students, this idea of a limit is just that stupid thing that you have to do at the beginning of the year before you can get to doing the real stuff where you take derivatives by formula. But for mathematicians, this is the thing. This is what calculus is. If there's a limit there, it's probably calculus. Mathematicians tend to call this analysis, but if there's a limit, there's probably some calculus hiding somewhere. Maybe. So these macroscopic things that we want to understand are really functions. So we have some function we want to know stuff about it, and we want to use this microscopic detail to learn things about it. What you all studied in your first semester, one of the things that you studied is the notion of the derivative. The microscopic thing that we're looking at, we take our function, let me do it over here, and we blow it up. And there, it looks pretty straight. It's not quite straight, so we blow it up a lot more, and eventually it looks like a straight line. So this is the notion of a derivative, which you are all intimately familiar with, and if you're not, you're in the wrong class, go away now. It's this idea of blowing something up and zooming in until it looks straight. What are we doing when we're zooming in? We're taking a limit. We want to understand what's going on at this point. And in order to understand that, we zoom in, zoom in, zoom in. And this process can be formalized by taking the limit as h goes to 0 of f of x plus h, maybe, let's call this a instead of x. Over h. And this gives us a thing that you know about, but you probably forgot this formula, called the derivative. This is not what we're talking about in this class, but this is what we will use all the time. And so this is one of the big ideas of calculus, is the idea of a derivative. What's another big idea in calculus? Yeah? Integrate. Okay, so integration. The idea in integration, we want to ask a slightly different question about the function. Not how is it looking in the small. We maybe assume that we know something about what's going on in the small. We want to know, it's sort of the same function. We want to ask the question, what is the area here? And we want to use the same idea, this idea, that in order to understand the big question, the macroscopic detail, we want to focus on a little thing, and then use those little ideas to put it together to understand the big thing. So in order to find the area here, this is my graph y equals f of x, and I want to find, I'm not going to shade it because we want, well, I'll shade it. We want to find the area there. And again, something that you all should know, and if you don't know, then you should be in Math 126 instead of 132, is the way to find this area is to chop it up into tiny little pieces. I'm going to use big pieces, but let's just chop it up. And so I chop it up into pieces. And instead of finding the area of the whole thing, I just find the area of the little thing. Well, if I look at this piece here, it looks almost like something that I can take the area of. But let's chop it up some more. So maybe I chop it up a little more. And if I keep on chopping, the pieces are very skinny, and then they have some little bit of curve on top of them. And I don't bother thinking about whether this curve is tilted down or tilted up or whatever. I just think this looks, I mean, to you, I can see that I drew the top tilted, but I doubt any of you can. Maybe you guys in the front can. So this is a rectangle. Just like in this case, this bit that's curvy, if I zoom in enough, it looks pretty straight. Here, if I chop it tiny enough, it looks like a rectangle. Rectangles are really easy to find the area of. You just take the height times the width, and we know the area. And so if we chop this thing up into tiny enough pieces, all we have to do is add up the area of rectangles. And that gives us the area of the big thing. Okay? So, what is the area of this rectangle? This should be a clicker question, but I'm not going to write it. Nobody knows really? Come on. Right. It's the height times the width. Well, we'll stick to width for a minute. What's the height? Well, it depends on where I am. But if this rectangle sits right here, and there's some point here, let's call it x star, sitting in there, then what's the height? Half of x star, right. And the width is, well, however much I chopped it up. Right? So if I put n rectangles here and I make them all equal, so if I used, well, let me use a number. If I used 100 rectangles, how wide is it? Nobody knows? Yeah, do that.
It's A plus B divided by 100.
Well, kind of. You're close. You're real close, yeah. Yeah, it's not A plus B divided by 100, because that would say this distance plus this distance over 100. Instead, it's this distance, which is this minus that, over 100. So you're close, but not quite. See, she knows all this stuff, so she can leave. If you know all this stuff, you can leave too. And if instead of 100 rectangles, we use n rectangles, then it's b minus a over n. Right? Now, let me point out one thing here about how this is working. I don't want you to memorize all sorts of formulas and stuff. I want you to think about what's going on. If you try and do this class by memory, you either have to have an amazing memory or you're going to screw up. And even if you have an amazing memory, next year or the year after you will have forgotten. But if you think about what the idea is and try and see how the formula fit together with the idea, this class is not so hard. Well, they're easier classes, but that's the way to succeed, is understand what's going on, and then the memory becomes easy because the memory is, oh, it's kind of like that, oh, it's this because that's how it works. But if you just memorize formula, you'll make little mistakes like a plus b over 100 rather than b minus a over 100, or you'll remember a wrong formula and you'll screw up. Okay. So, this is the width, fine. So now, oh, good, that one works. So now if we want to find this area, well, the area with 100 rectangles is going to be, well, we take 100 points scattered along there. Let me just call them, so let's call them x1, x2, x3, I'm going to forget about the star, up to x100, soon I'm going to change the 100 to an n, is going to be, well, I take the height, f of x1, and I take the width, which I'm going to write out here, b minus a over 100, and I multiply them together. And then I take the next guy, f of x2 times b minus a over 100, plus f of x3, blah, blah, blah. I just go. I'm not going to write all 100 of them. And then I get to the last one, and I multiply it times the width, and that's what I get. So this is my approximate area. It's not the actual area, but it's pretty darn close because there's 100 little rectangles there. They're all very skinny. It's really close. This is tedious to write. Most of you probably are familiar with sigma notation. Anybody not familiar with sum notation? This thing? You're not familiar. Okay, so I will now introduce it here. We're going to use this notation a lot, but probably not until October. We'll use it a little now, and then we'll use it a lot in October. So this is tedious to write, and if instead of 100 I had 1,000, it would be even worse. And if n, I wouldn't even know what to write. So, but we're adding a bunch of things. And they all look kind of the same except for one little change. So this means this is a Greek capital S, standing for sum. And the things we're going to add up, well, we're going to add up little n thing. Let me use I because I used n somewhere else. Starting from 1, and here going to 100. And what are we going to add up? We're going to add up f of x sub I. So this notation means exactly what is in the parentheses. So these are exactly the same thing. There's no math here, there's only notation. This is exactly the same way to write that. So this big sigma shouldn't be scary. If you program, this is a for loop. A for loop with a sum. So this is for I from 1 to 100. What language should I write in? How about, I don't know, basic. Do sum equals f of it equals old sum plus f of x sub I. And do. There we go. So this is just take this thing, add it. Take the next thing, add it. Take the next thing, add it. We will study these in much greater detail in about 6 weeks, 4 weeks, some number of future times. Okay, so that's the area with 100 rectangles. If we change it to 1,000 rectangles, it doesn't look a whole lot different. What? Oh, yeah, thank you. There's another 0 I missed. I'll do that kind of thing a lot. It's pretty much the same. So in general, the area is going to look like b minus a over n, where n is 100, 1,000, 1,000,000, 5, whatever you like. Let's put the sum on the outside. I equals 1 to big N. Here, n is 1,000 times f of x sub I. Now, we haven't used this idea of limit yet. I'm sort of at a picture at this level. The area is very close to something straight, but it's not exactly equal to something straight. So now the thing we do is, instead of taking the limit, well, we take two limits sort of at once. The rectangles get small and the number of them gets big. So the area, actually, we know that the area is going to be just about b minus a over n times f of xi sum I equals 1 to n. And we can show, and I'm going to skip over that, because you can spend a lot of time, maybe I'll, whatever, that it's going to be less than a sum of this form, depending on how we choose the xi, and bigger than another one, and these two things go together. Let me draw that picture, actually. So let me do n equals 4. Here's my function. I want to go from there to there. I want the area. I'm going to chop it into 4 pieces. There we go. And I can certainly find, I didn't tell you how to choose these xi's except that they live inside this region somewhere. So I get to choose x1 in here somewhere. If I choose it here, this is x1. And then I choose x2, well, it looks to me like I want lowest. Here, this is my x2. And then I'm going to choose it here. This is my x3. And then I'm going to choose it, looks like about here. There's my x4. Then the area I will get will be definitely too small. But for sure, it's absolutely too small. It can be no bigger, no smaller. Because everywhere, the little rectangles, or the big rectangles in this picture, sit underneath the curve. So this is a lower sum. So this is a lower bound. The area is for sure, even if I know nothing else about the function except the value here, 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 and here, the area is for sure less than what I get with those 4 rectangles. Bigger. Those 4 rectangles are less than what I get for the area I want. But I can play a different game. Let me just draw the same picture, or pretty close to the same picture. Here, 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 there. So if instead I chose, maybe instead of calling them x, I'll call them, I don't want to call them y, v. I'm going to call them m. M for, well, max and min, but whatever. I will call them v. If I instead choose this point to be my first one for this rectangle, and then I choose, well, it looks almost the same, but this point to be my v2 here, and then I choose this guy to be my v3, and then I choose this guy to be my v4, then I get something that is for sure too big. Right? Now, this should be reviewed to all of you, but maybe you forgot it, whatever. So that means that, you don't need to see that. So that means that the area is between, and maybe it's equal, but probably not, the sum, I equals 1, I use 4, of, I didn't give these numbers, but b minus a over 4 times f of xi and b minus a over 4 f of vi. Right? The actual area is between those two numbers. Does everybody agree? No matter what the function looks like, as long as I choose those according to the rule I've shown, the xi's are the minimums and the vi's are the maximums. Okay? But there's nothing magic about 4. Could have done the same thing with 40. Or 400, or 4,000, or 4 million, or just some number n. And I would still get the area is trapped between those two things. So now, the magic trick is, but notice also that if I use lots and lots of rectangles, and the function isn't too crazy, this will get bigger. If I use twice as many rectangles, then I get a taller one there. And I get a taller one here. And I get a taller one here. And I get a taller one over here. So I would get a bigger area on the bottom and a smaller area on the top. And so, as we take more and more rectangles, these two numbers go to the same thing. So if we take the limit, bing bong, doesn't matter, as n goes to infinity, let's do this one. Of either of those, or any other way of choosing them, then this goes to some number. So if this number exists, this is the area. And we call this area the integral. So the integral is this area. Oh, I never stopped these things. Shame. Oh no, I didn't. I did stop. Right, the integral is this area. So this is the definition of the integral. If we chop it up into a bunch of rectangles, choose a point inside the rectangle, and take the limit as the number of rectangles goes to infinity and the width goes to 0, this gives us a thing called the integral. And it's the area. Wow. Okay, I'm way behind. That's all right. So why did I go over this? Because you already covered this before. This understanding that when we're doing these integrals comes down to looking at little slices is extremely important for understanding what we do later. So even though, just like when we did derivatives, after a little while you stop using this formula. If you think back to when you did calculus 1 or calculus A or whatever you called it, you used this formula for a couple of weeks or a month or whatever, and then your professor showed you a magic trick that you never need this formula anymore, and he said, geez, why did I sweat so hard to do that formula? And similarly, when you learned about integrals, they probably made you add up little rectangles over and over and over, and you're like, God, I hate this stuff. And then magic happened, and there's an easy formula. What we like to do in math is take a hard problem, understand it fully, and then make it easy. If we start with the easy, then when we try and apply it to something else where the original problem doesn't fit, up the creek, it's not going to work. You don't know how to adapt it. So it's important, and we keep emphasizing this definition because this is what's really happening. It's like if you have a car, there's a motor in there. If you have an airplane, there's a motor in there. The same principle, well, kind of, maybe not an airplane, how about a boat? The same principle that makes the boat motor and the car motor run is the same. If If you have no idea what's going on in a motor, you'll think that a boat motor, driving a boat and driving a car have nothing in common. Well, boats might have sails and so on. It's a bad analogy. But the motor, the thing that makes the motor go is the same. There's little explosions going on, pistons jumping up and down, and all that sort of thing. This is the motor that makes it work. And when we want to change this to make our motor not calculate areas, but calculate something else, we need to understand that's what's happening. So, I want to emphasize this because if I just start with, which you can probably all do, what's the integral of x squared? You all know that it's 1/2 x cubed plus, I think you all know, 1/3. If I wrote it, it would be right. You all know how to do that, I hope. I should clicker question you and find out. So you all know how to do this thing, but some of you have probably forgotten this part. Or just remember, God, it was some horrible thing that they made us do, and I hated it. That's why I'm in 132 instead of 126. You're not going to make me do this. So, just reminding you so that I don't have to make you do it until later. Okay, so, given this business, without even knowing yet how to calculate integrals, we know some stuff about integrals. Because integrals are areas. Well, one observation that we can make here from this picture is, so the way we define this only works if the function is positive. If the function is negative, it's not really an area. Right? If my function goes like this, then we like to think of this area as being a positive number. Now, how much? If we ask what is the area of, if you want to know the area, because I'm going to put carpet over this thing, I don't want to buy 0 square feet of carpet, but the integral, if I drew it pretty close, if I drew it right, it is certainly possible. So, let's add a little more. Now it makes sense. So, it could be true that the integral from 0 to 5 of this function f of x is 0. If you use the formula, you may come up with 0. Yeah, let's move it down. It's okay. It may be 0, but the area is not 0. That's because, if you think about this definition, in this part, your rectangles have a positive height. But in this part, your rectangles have a negative height. Maybe I should write it positive. Because the formula does not say take the absolute value of the function, which is the distance from the graph to the axis, but just take the value of the function. So if we wanted area, we have to change the sign here. But if we want integral, then we think of this as negative. We think of this as positive. So integral, by this definition, without putting little absolute values there, is not actually an area. It's a signed area. And that's actually, that may seem like a defect, and it is a defect from the original design, but it's easily remedied. The problem is discover how much carpet I need to cover this area. But the integral is more than just a way of finding area. It's a way of averaging, a way of finding distances, a way of finding all sorts of things. And we can easily correct it by just taking absolute values. So it's not a defect that something with a positive area in the sense of perfect needed has a zero integral, right? Okay. And notice I didn't even tell you how to calculate anything. It's just built into the problem that this is going to be negative. Because it's below. The way we do it, it's negative. And we can do some simple integrals without this, I can. No, I'll leave that there. In some cases, and you probably did, and on the homework assignment there are some of these things, you can calculate the integral without being able to, without having to calculate the limit. For example, let's take a specific function. F of x is absolute value of x. The graph of absolute value of x looks like this. So, let's make this be a flipped question. The integral from -1 to 1 of absolute value of x dx is a 2, b 0, 3, 1. That's not a c. C 1, d -1. About e. We need some formula. Okay, so this is a last one's an e. Last one is E. A, B, C, D, E, 5. Okay. I hope the right answer is there somewhere. Well, your clicker says 1A. So do it by letters or do not, if your answer is C, do not click the button marked 1. If your answer is C, click the button marked 3. Sorry. Which should also say 1/C. Yes, it does. So do it by letters. Because there's no number called the no. Anybody need more time? Okay, so I'm going to stop this now. Last chance. Here we go. Wait. Oh, come on. You didn't answer when I said you need time. Too bad. Okay. So, it seems that 14% of you think this is the right answer. I could show you the graph, but I won't. 12% of you think this is the right answer. 75% think that's the right answer. Everybody knows. Nobody doesn't know. So most of you think that it's C, and most of you are right. It's unfortunate for those of you that think it's those. But if you just look at this picture, this is a question about area. What is the area of this triangle? 1/2. The height here is 1, because the absolute value of 1 is 1. The width is 1. So this area is 1/2. Over here, this graph is above the axis. So its area is also 1/2. You could also think, cut this out, lay it down there, you get a 1/1 square. If the area of a 1/1 square is not 1, something is very wrong. So the answer is, in fact, 1. But don't worry, we'll have more chances. So, here, let me give you another chance. We have another few minutes. None of these are the questions I prepared. Cool. Let's make it So, suppose we do the same thing. Instead of absolute value of x, let's just do the integral from 0 to 1, no, not 0 to 1, negative 1 to 1 of x dx. I don't have to draw the picture, I hope. The choices are A, 2, B, 0, C, 1, D, negative 1, E, can't say. And F, a rabbit. So we have at least one bold person who answered rabbit. So that person is either bold or doesn't know how to work with clicker. Or his clicker, I don't know. Okay? Everybody's answered? Everybody's picked the rabbit? Oh, more people. Oh, somebody just changed their mind. Change them right back. Come on. Okay, I'm stopping this now. If you are no longer bold and want it there, that person put it back. Good for you. All right. You're stuck with it now. Okay, so the correct answer, favored by 84% of you, is in fact 0. Because the graph of y equals f, the graph of y equals x looks like that. This stuff is plus, this stuff is minus. We're going from there to there. They cancel out, we get 0. Another property or two that we can use. Yeah, I'm going to have to extend the review too. That sucks. Is we can break up integrals because they're areas. If we wanted to find the area, this is always the function I use. If we wanted to find the area of that thing, we can integrate from here to here, and then integrate from here to here. So this is A, this is B, and this is C, and this is f of x. Then, for sure, the integral of f of x from A to C is the same thing as the integral from A to B, plus the integral from B to C. Right? We can break up integrals. Obviously, if its width is 0, the integral is going to be 0. So something like the integral from 3 to 3 is sine pi x squared. Oh, let's just do pi x. Dx. No, 3. What is this? 0. Better be 0. Doesn't matter what function I put here, because we're saying, okay, we have this function sine pi x, and we're 3 pi, so we must be here. And we're saying, what is the area of that line? The area of that line is 0 because it has no width. Right? This is the area of the line. One last thing, and then I guess we're out of time, is this has an ordering. We always put the smaller number on the bottom and the bigger number on the top. If we switch them, it changes the sign. We go backwards. So once in a while, we end up going backwards, and we will do some of this going backwards later. So the integral from A to B same thing as negative as the integral of b to a. So I will continue and I hope finish this review on Wednesday. We have no class on Monday because it's Labor Day. The homework due a week from today